Dr. Dave Williams is going to talk from ASU, researcher in planetary science. He's going to talk about roving the solar system.
Okay, thank you very much. Always a pleasure to come back here. First let me introduce myself since there's people who probably never heard of me. My name is David Williams. I'm an associate research professor in the School of Earth and Space Exploration at ASU. And I work on several NASA robotic missions exploring the solar system. As a student, I worked on the Magellan Venus orbiter, looking at the radar data of the surface. I worked on the Galileo mission during the Earth-Moon flybys when we did the first multispectral studies of some of the deposits on the far side of the moon, which we couldn't see from Earth. Then when I came back to ASU back in 1998, after I got my PhD, I worked on the Galileo mission when it was out of Jupiter, in Jupiter orbit, and did a lot of work on the Galilean satellites. From there, I went to work on this mission. This is the European Mars Express orbiter. It has a German-built stereo camera that has produced all of these images you see here in my screensaver. And I continue to work on that mission. I've been funded for over a decade to continue to work on this, studying the surface of Mars and producing these wonderful stereotopographic views. And most recently, I work on NASA's Dawn mission when it visited the asteroid Vesta, the second largest asteroid in the main asteroid belt. And I worked on that mission. Well, they're sort of continuing to do the data analysis. Dawn left Vesta back in September of 2012. It's now on its way to Ceres to get there in March 23rd of 2015 is the arrival date, plus or minus a week. So those are the missions I work on. And back on that table over there are a series of posters. There's two different views of Vesta posters, a Galilean satellites poster celebrating, last year was the 10th anniversary of the end of the Galileo mission at Jupiter. And then there's also a double-sided Mars poster with a lot of these images on it. So please feel free to take them. There's rubber bands there. Those are my gift to you for attending. I want to mention a couple of things here. There's also back there this brochure about the Arizona SciTech Festival going on this month. ASU's part of that is called Night of the Open Door. And for the Tempe campus where I work, it's going to be on Saturday, March 1st from 4 p.m. to 9 p.m. And then all of our labs at ASU are open. My laboratory that produces these posters, the Planetary Imaging Facility, is going to be open. Our new building with the Gallery of Scientific Exploration is going to be open. Professor Phil Christensen's Mars facility, Professor Mark Robinson's Lunar Reconnaissance Orbiter Camera facility are all going to be open. We also are going to be giving a series of talks in the different buildings on campus, covering everything from the Dawn mission to cosmology to exoplanets, to engineering to facilitate future exploration. So,
open house this Friday of some sort?
I think there's an astronomy open house. Yeah, they do those once a month. Yeah, so if you go to our website, cc.asu.edu, and if you go to the top page, you should see a link for Night of the Open Door, and you can see all of the events that are going to be there. So if you have any questions, you can ask me afterwards. Okay, so yes, the topic of today's presentation, I'll just click this on here. I upgraded my laptop software a couple of weeks ago, so things are always a little bit interesting when I do that. So yeah, the title of this presentation is called Roving the Solar System from Lunakhod to Curiosity and Beyond. So before I begin, I always like to start, for those who aren't familiar with robotic exploration of the solar system, to try and tell you the rationale about how we explore the solar system. And we do it through a phased approach. We do what's technically possible, what we have the engineering skills to accomplish. We do what's affordable, what we have the money available in the budget to do. We do the easy stuff first, accomplish it successfully, and then move on to the more complex missions. And in order of increasing difficulty and complexity, this is the series of robotic missions we undertake as we explore the solar system. The easiest thing to do is to send a flyby. A spacecraft just flies by a planetary body, takes pictures, collects data as it goes by. The next hardest thing to do is to send an orbiter, something that can actually slow down and get into orbit around another planet or moon or something. And the advantage of an orbiter is that from a continuous orbit, a consistent orbit, you can get your consistent global data set. You're able to collect data and get a truly global characterization of the body you're orbiting. So once you have your orbital data, the next thing you want to do is actually land on the surface. And there's various ways you can land. You can smack down on the surface, take pictures as you descend, but then your instruments are broken when you're on the surface. That was like the Rangers from the 1960s when we first started exploring the moon. So then you want to learn how to soft land. And that's where you use retro rockets or parachutes if it has an atmosphere to slow down so that your lander is on the surface and all the instruments work, and then you can analyze the soil or everything around it. That was like, say, the Surveyor program prior to the moon landings, Apollo moon landings. So, okay, you've landed on a surface and you've measured all your stuff right here at your landing site, but what about the stuff you see on the horizon over there, over there? So you want to get over there, you need some form of mobility, and that's where the rovers come in, which is the subject of this talk today. Mobility on land, or if it's a body that has an atmosphere, you can use the atmosphere for mobility. So the next hardest thing to do is to take a sample of the soil or the rock or the ice or the atmosphere and bring that back to the Earth where we can more thoroughly study it in our laboratories on Earth. And that's where we have sample return. And we have done that for several bodies. And of course, the hardest thing to do is to send humans to orbit and then land on planetary bodies. So, you see here, this is the status of solar system exploration as it stands right now. You see those different modes of exploration as you go across the top. And then here you see the major bodies of our solar system going from Mercury all the way out to Pluto. And for the purpose of this talk, Pluto is a planet no matter what the IAU says about that. As you can see here, we've done telescopic observations of everything, of course, to discover these bodies. We've done flybys of everything except for Pluto, but we have a spacecraft on its way out there called New Horizons, NASA medium-sized mission. It will get to Pluto, do its fast flyby in July of 2015, and then hopefully sometime after that fly by a Kuiper Belt object out beyond Pluto. Orbiters, we've had orbiters around all the inner terrestrial planets. We've had it around Jupiter, around Saturn with the Cassini mission that's operating right now. There's another Jupiter orbiter on its way out there now, and this year we have a European mission called Rosetta, which is going to orbit and land on a comet. So that'll be a very interesting mission. These yellow ones out here are concepts. Those are the next major things that we would like to accomplish. The Europa Clipper would be a Jupiter orbiter, would do many, many Europa flybys, effectively do the same work that an orbiter would do, but without having to deal with the intense radiation close to Jupiter. This one that's lit up in green here called JUICE, that's the Jupiter Icy Moons Explorer. That is going to be the European Space Agency's first L, or large class mission. That's going to be an orbiter of the moon Ganymede, the largest moon of the solar system. Did anybody see online and the science websites or from JPL that they released the global geologic map of Ganymede this week? Combined Galileo Voyager data. I was one of the reviewers of that map, so very happy to see that come out. Landers, we've landed the Soviet Union, landed on Venus, the Venera series. They also had a robot on the moon, we of course had the Vikings, many, many types of landers throughout the solar system. We had an atmospheric probe into Jupiter, and we've had the European Huygens probe landed on Saturn's largest moon, Titan. Rovers, the subject of this talk, this is what we're going to explore in depth here. The Soviet Vega balloons at Venus, their Lunakhod rovers on the moon, and the various Mars rovers on the surface of Mars. Sample return, the Soviet Union had the 3 lunar sample returns, robotic sample returns. We've had sample returns from asteroid and cometary material, and we're now in the planning for the Mars sample return mission next decade. And of course for human missions, the Apollo program. So what I like to say is the goal is to completely fill in this chart. We'll have completely explored the solar system. Then we can start living Star Trek and boldly go where no one has gone before. So why rovers? The advantages, as I said, mobility, access to multiple sites or locations on a planetary surface. It allows higher spatial resolution of features on a surface than you can get from orbit, and you can do what we call in geology in situ studies, direct measurement of rock, soil, ice, or atmosphere compositions and physical properties. And there are various types of rovers. There's ones that have wheels, we call drivers. One with legs, we call walkers. Ones that can jump, we call hoppers. Ones that float through the atmosphere, balloons, floaters. And then ones that can fly through the atmosphere are called planes. And I'll talk a little bit about those. The walking rovers, or driving rovers, excuse me, you see right here, this is basically what we have actually successfully deployed. This is the Soviet Lunakhod rovers on the moon. Here's the Sojourner rover from the Mars Pathfinder mission back in 1997. Here is the Athena-class rover. That's the Mars exploration rover Spirit and Opportunity. and here is the Curiosity rover. So those are what we'll spend most of our time talking about, but I wanted to mention these other concepts as well. Walkers are things that have legs. This is an artist's concept of a pressurized walker for the moon, something like the old Imperial walkers from The Empire Strikes Back. Here you see some micro rovers here that are sort of like insects. These have not been deployed actually, but are an engineering study. Now the idea of a hopper is something for a low gravity body. We had a recent Discovery mission proposal for a mission that was not selected called Chopper or Comet Hopper. This would be something that would land on a low gravity body like a comet, and then it would have thrusters to just sort of bounce up, shoot up, and land in another location, and just do that periodically. If you have a jet from the comet push it away, it's still dense enough that it would come back onto the surface, even with low gravity. So it would sort of do roving by hopping across the surface. This may be proposed again at the next Discovery opportunity, which currently may happen sometime later this year. Flying rovers, balloons. We'll talk a little bit about the Vega balloons. These are actually French-built balloons that were deployed by the Soviet Union in the atmosphere of Venus. So these actually, here's what one of them looks like. Here's what they actually, have been operational. These are concept balloons for Mars and for Titan exploration. So that is getting a lot of serious consideration. Flying rovers or airplanes, we're all familiar with the use of unmanned aerial vehicles for science and military applications. You can extend that to develop something that might be able to explore another body with an atmosphere such as Mars. This has been proposed, but it was not successfully funded. So to summarize where we're at with planetary rover missions, in terms of time, the Soviet Lunakhod rovers, Lunakhods 1 and 2, these were operating about the same time as the Apollo human landings on the surface. The Vega balloons in the atmosphere of Venus, one of them lasted 46 hours at 54 kilometers altitude. Then we get more U.S. dominated until recently with the successful Mars program of rovers. We'll talk about each of these rovers in detail. And then most recently, the Chinese, the People's Republic of China, successfully landed a rover on the moon, their Chang'e 3 mission, just last December, and that was also a driving rover. I'll show you some pictures of that. Upcoming missions, the European rover ExoMars, and then the Mars 2020 rover to begin the Mars sample return campaign. Okay, here's Lunakhod right over here, this picture again. It always reminds me of those old Wile E. Coyote Roadrunner cartoons where he puts together from Acme your grandmother's bathtub on roller skates to drive around there. But Lunakhod 1 and Lunakhod 2, as you see right here, solar powered, and they both successfully landed robotically on the surface. Now, these particular rovers were operated by telepresence, so you have a controller at a joystick on Earth, and because the time delay to the moon is only 3 seconds, you're able to drive these things. And here you see actually tire treads here. Here's where you have one of the physical properties probes measuring on the surface. And this is for Lunakhod 1. Here's the lander where it drove off the ramps, and here's another view of it. Operated for 322 Earth days, traveled about 10.54 kilometers, returned more than 20,000 TV images, performed 25 lunar soil analyses. It had an X-ray fluorescence spectrometer, which allows you to get elemental abundance of surface materials. So this is sort of their consolation prize. I would, after we sent successful Apollo astronauts to the surface of the moon. But they did do some good work. Lunakhod 2 operated for about 4 months. Here you see a couple of the photos from it. Here's one of its probes right here. Traveled 37 kilometers. It did hold the long distance record that has now been broken. I'll talk about later. Returned more than 80,000 TV images, high resolution panoramas, did a lot of mechanical tests on the surface used for laser ranging and other experiments. And for those out there, which I'm sure not in this audience, if you didn't believe that those vehicles actually existed, the Lunar Reconnaissance Orbiter camera, the NASA mission currently orbiting the moon, we operate the camera from the ASU Tempe campus. We've actually located the rovers on the surface. You can see the rover and the rover tracks right here. Here's one of the landers. So kudos to the Soviet Union for being able to execute that back in the 1970s. Since we're at the moon, I think I'll mention now about the Chinese lunar lander. Chang'e 3 landed in December of 2013. They had the first soft landing on the moon since 1976. Here's a cartoon of their lander and their rover called U2, or White Rabbit. This was the landing zone here. For those of you familiar with the near side of the moon, this is Sinus Iridum up here at the northwest corner of the Imbrium Basin. And here's the LRO view. So here's where the intended landing site was, and I think this arrow is where it actually ended up landing on the surface. This is a pretty interesting area. It's, the Imbrium Basin is flooded by volcanic Mare lava flows, and you have punctuated by craters here. Here's the Laplace A crater, and when you look at it up close, you see it's got this impact melt in the surface there. The heat from the impact actually melted the material there to produce this sort of flow-like material. So very interesting. Now, here's the pictures from the Chinese mission. You can see the lander looking off on the horizon, and there's the deployed rover on the surface, the fact that it actually has driven on the surface. Here's the rover looking back at the lander, and then the lander looking down at the rover. So these are all public images. If you follow this type of stuff, you've probably seen it. Here's identification once again of the landing site over here. Here's another view of the rover, driving on the surface. This is a movie. This is looking at the same location from the Lunar Reconnaissance Orbiter camera, and you can see there this is a flashing, and actually you can see the lander on the surface right there. So we pinpointed its location.
And there's two things there.
It was a movie. It was flashing back and forth. Did you see?
Well, yeah, but there's actually two. There are the rovers right below it.
Okay, right here.
Right there.
Yeah. So that's the lander, and that's the rover. Yep, right there. And this is just another view. So here you see, this is just showing some of the geology. You have a wrinkle ridge right over here. You have the darker Mare lavas over here. Probably a compositional boundary between here and here, just based on the albedo or brightness of it. And then just another high-res view looking at the lander and the rover location. And this is just how they figured out exactly where it was located, just based on the surface features that the lander saw, and then correlating that with the orbital imagery. So that's all I really have to say about the Chinese lander. It lasted, I think, the first time in lunar dark, and then it came out, it functioned, and then it went in a second time, and it's just now come out, and they have been able to communicate with it, although it has mechanical problems. I don't know if it's going to continue to rove, so you have to stay tuned to the press about that. Now, the Soviet Union did try to land a rover on Mars back on the Mars 3 mission. This was launched in May of 1971. Here's what the spacecraft looked like. Here's what the landed component looked like. Here's what the rover looked like. And I think it's actually on here. It would actually would have been deployed from an arm and be attached with a tether, and it's got a skis on the surface here. Unfortunately, it landed on Mars in a dust storm on December 2nd, 1971. And so the arm would have put the rover on the surface, attached the lander by umbilical, and used skis to move around. However, contact was lost 14.5 seconds after landing. No usable data was returned, and best evidence is the rover was never deployed. So the moral of the story is never land on Mars in the middle of a dust storm. Of course, they couldn't do anything about it at the time, I imagine. Okay, let's jump a couple of decades to the first successful NASA mission, the 1996 Mars Pathfinder mission. This is the mission after the Viking landings on the surface. So here you see the landed part on the surface. This is where you use the airbags. You bounce around, the airbags deflate, you open up like a flower petal. Here's the camera on a mast over here on the lander called the Carl Sagan Memorial Station, named after him because Carl Sagan died back in 1996. And here's the Sojourner rover, which was deployed. And here you see the panorama of the ramp, and the rover had gone down and it's snuggled up right against the rock named Yogi. This picture over here, this is a windsock experiment was attached to one of the panels, and you can see that it's basically a pole, and there's smaller poles with these little cones on it. That was actually built in the basement of our building at ASU. It's a windsock experiment to measure wind direction at speed at several elevations above the surface of Mars. And my late supervisor, Professor Ron Greeley, designed and built this here for this particular mission. So here's the panorama, another part of the view of the landing site. You see the Twin Peaks in the distance. This landed in Ares Vallis on Mars. It was chosen because this particular landing site is thought there was a catastrophic flood of water that erupted out onto the surface and transported a wide variety of rocks on the landing site. And that was proven by the Sojourner rover with its alpha proton X-ray spectrometer. it nudged up against this rock here, Barnacle Bill, found out it was sort of an Icelandite. It's a more silica-rich volcanic rock compared to Yogi, which was more of a basalt like we see in Hawaii. So it successfully tested the airbag concept for the later mission, the Mars exploration rovers. And you'll recall that it was actually 10 years ago that those rovers landed. Spirit was the first one to land in early January of 2004, 10 years ago. It landed in this giant impact crater called Gusev, which they thought would have been flooded by sediments. Instead, they found it was actually flooded by volcanic lavas. So it landed at this point here. They named it the Columbia Memorial Station after the Columbia astronauts, and then it explored this crater, found basically basalts until it climbed up to these Columbia Hills over here and found the rocks up there were very pyroclastic or explosively emplaced volcanic materials that had been modified or altered by a flow of liquid water. It descended from the hills and then explored this volcanic feature here called Home Plate. You can see the tracks and get almost completely around there before it got stuck in a sand dune down over there. Here's a view. This is from the camera looking down on the rover deck, and you can see the solar panels here covered in dust. And this was back in 2008. So this was a big problem for the mission. The dust accumulates out of the Mars atmosphere on the solar panels, but you would get occasional dust storms, dust devils that would blow the dust off, and then you could generate more power and keep going. That's why these rovers have lasted so long on the surface. As I said, Spirit got stuck on May 1st, 2009, 5 years, 3 months, 27 days after landing. It lasted 21.6 times longer than the planned mission duration of three Martian months. So the last communication was on 2010. It traveled a total of 4.8 miles on the surface. And here you can see the deck, and it's stuck in the dirt down there. Now, on the other side of the planet, the Opportunity rover landed in a place called Meridiani Planum. This was a landing site on Mars that, through orbital data, Professor Phil Christensen of ASU, his thermal emission spectrometer, indicated that this area was dominated by hematite, which is an iron oxide that often, but not always, forms in the presence of water. So this landing site was chosen. It's also very, very flat, like a parking lot. So they landed Opportunity here. It actually went into this very shallow crater, Eagle Crater, the 3 million mile hole-in-one. And then from there came out and has been exploring the outcrops that are penetrated by craters all through this region for years. So went from there down to Victoria Crater, spent time there, from there down Santa Maria, and then all the way down to Endeavour Crater. And this rover continues to operate to this very day. It is now going on this inside ridge here, which is part of the rim of Endeavour Crater, and exploring the rocks at this location. This rover, over the course of its lifetime, viewed dust devils on the surface and discovered iron meteorites on the surface of Mars that it analyzed. This is a landing site that it explored, named after Professor Greeley of ASU, who passed away in 2011. And it is now broken. This was just before, I think, but it just broke the record of the Lunakhod 2 rover. So Opportunity has traveled the most distance on the surface now. And it continues to give back. Just in January of this year, it was announced in the journal Science, Opportunity identifies a past habitable environment. It looked at these rocks on this ridge, this part of the rim of Endeavour Crater, a place where the orbital data suggested there might be smectite, which is clay mineral, and Opportunity confirmed the orbital detection of iron and aluminum-rich clay minerals in Endeavour Crater. These are Noachian age, that's a Martian geologic time period, greater than 3.7 billion years old. They underlie younger rocks indicative of more acidic environments. This is what was found earlier in mission. But these clay minerals indicate that you had a habitable environment much older than those found at Gale Crater by Curiosity. So I have another location on the surface of Mars where the rocks are telling us that the waters that flowed at this point were not too acidic, not too basic. They would have been ideal for microbial life had it evolved on Mars. So Opportunity continuing to run. Now let's talk a little bit about the Mars Science Laboratory mission, the Curiosity rover. So the science goal of the Curiosity rover is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, past or present. And these are the science objectives: assess the biological potential at least one place for organic carbon, search for the chemical building blocks of life, identify the textural features in rocks, indicative of biologic processes. Characterize the landing site geology at all scales, looking for the chemical, the isotopic, the mineralogical composition of surface and near-surface materials. Study the rocks and soil. Investigate the planetary processes relevant to past habitability. The timescale of atmospheric evolution, the role and distribution of water and carbon dioxide, and then finally assess the radiation environment for the time when we're going to be sending humans to the surface. This is just a chart. This just lists all the science instruments, but just pointing out it has lots of cameras, it has lots of spectrometers, radiation detectors, environmental sensors. When you look at the Curiosity rover, here's the breakdown. So you see it's the 6-wheeled rocker bogie suspension system, the rover deck. It's got a mast that has the cameras in it, radiation sensor. It's got the laser ablation spectrometer called KenCam. It's got a robot arm right here, and it's got your elemental abundance. It's got a color hand lens imager. It's got the brush, and it's also got a drill on it, and it allows you to drill a 4-centimeter drill core on it and deposit it into the instruments on the deck here, which allow you to determine the composition. What are the do's and don'ts? It is not a life detection mission. It's not designed to detect present-day microbial metabolism. It does not have the ability to image microorganisms or their fossil equivalents. What it can do is detect complex organic molecules in rocks and soils. It can identify the isotopic composition of inorganic and organic carbon, and it can search for the chemical or textural patterns of biological versus physical processes, because microbes that produce minerals will have them in a different shape or structure compared to that produced inorganically. So where did we land on the surface? Well, you know the answer to this already, but I'll just say that the science community here in the United States who studies Mars put a big list of possible landing sites. They narrowed it down to 4 of them here. They all have unique attributes. Evers-Wally crater had a river delta in it. Gale crater, it had this mountain of sedimentary material. Holden crater is the outflow of a major channel. Marth Vallis is a very old phyllosilicates, clay minerals section. And so they went up to the NASA administrator, and the best case was made, and the winner ended up being Gale crater, because the rover, once it lands over here in this landing ellipse, could then drive and explore the materials out here and then go up through the sedimentary sequence of rocks and understand a great deal about the evolution of Mars by studying those rocks. So here's what the rover looked like in its back shell when it was packaged in there on October of 2011. This is a very large rover. Here's a couple of engineers for scale. So the Sojourner rover was the size of a microwave oven. The Spirit and Opportunity are about the size of a golf cart. This is about the size of a Mini Cooper, 1 ton. It's so heavy, it was too heavy for airbags, so they had to find another way to land on the surface. And you've probably seen some of this. Here's the descent imager watching as the spacecraft is landing. It just jettisoned the heat shield, and now the rover is descending as it's getting closer and closer to its landing site. This is a field of dark sand dunes right next to the landing ellipse. And you can see here it's getting closer and closer. It's going to start firing the retro rockets. And gets closer and closer, and then you see the retro rockets fire to slow it down, and then it drops down the rest of the way. The wheels are deployed, and it makes contact. So, and that's just showing the heat shield impact, a couple of different views of that. So that was the landing. We all remember that. And yes, as you recall, it was a picture-perfect landing on the surface. This was during the last Olympics, when it actually, last summer games was when that went on. So that's why that cartoon is there. But it's really cool what we can do now. Here's a view of the landing from the Mars Reconnaissance Orbiter with its high-rise camera. And you can actually see here, here's this view right here. You can actually see the rover is still in its back shell here, and it's connected to the parachute, the supersonic parachute that slows it down. So one robotic spacecraft orbiting the planet Mars is actually imaging another robotic spacecraft in the process of landing on Mars. That was Sunday, August 5th, 2012. So this is just a view from the German stereo camera that I work on of Gale crater, showing you here's Mount Sharp, the mountain in the middle of this crater, and here's the landing air ellipse. So it landed right in there where that blue dot is, right over there.
Question on this?
Yeah.
I always got confused. I think because I had seen this image too much. This is looking south, isn't it?
Well, since the stereo camera, the way it's put together is that, you have the nadir view, forward and back looking stereo, and the color channels. You put them together in a computer, you make a digital terrain model, and you can rotate the view of the image any particular direction.
Because I always had this impression the rover is in the south half driving north towards the peak in the middle, but I think it's the other way around, isn't it?
Well, there's no north arrow, unfortunately, in this slide here, so I'm not sure which direction is actually north, south, east, and west on Mars. But yeah, the path that it's taking, as you'll see, is, it's going basically around. It's trying to avoid most of these sand dunes, go through the thinnest spot for when it actually starts climbing. It's going to climb up the low slopes and proceed.
I had an impression, because I had seen this early on, and that was in a northward direction, but from some of the other mission statuses, it's actually going.
Mm-hmm. We'll see if in some of the other pictures if it actually has the north. Normally you're supposed to put north arrows on things there. Here's a view from just after landing. So you see, here's where the lander is. The dust from the retro rockets blew away some of the lighter colored dust, exposing the darker material. Here's where the back shell and parachute hit. Here's where the heat shield hit. And the sky crane, after it released the rover, it flies away, and then it crashed in this location over here. So the first 6 to 8 months of the mission after landing was just commissioning, slowly checking out all of the systems on the rover to make sure that they operated properly before they did any real science. So here, these first views here you see the wheel on the surface to make sure you're there. You see the mountain in the distance. Here's the sunlit view, so you can see the whole rover on the ground with Mount Sharp in the distance. And just watch the dates as you look at these different images, because most of them are just going to be within the first weeks to months. Here's the test of the hand lens imager. It still has the dust cover attached, looking off into the distance. The first 360-degree panorama on the following Wednesday. The first color image of the ground. The first view of the bedrock exposed by the retro rockets. Here's another 360-degree panorama. Here's a large color view, and here's where the retro rockets have blasted the dust away from the surface. The first high-res views looking at those particular areas and actually seeing there's outcrop right over there that it's looking at. Here's a view of the wheels. Here you see, looking off into the distance, you can actually see very well the Mount Sharp, and you can see all the different sedimentary layers that the rover is going to be wanting to travel and investigate. So, and here's the dunes in the foreground. So here you see, this is for the first teleconference they had on August 17th, the landing site. And it's interesting, you have 3 different geologic terrains here, just by the way that it looks. You have this one over here, you have this one over here, and then you have this one over here, this brighter thing. So 3 terrains coming in together. So this was the first place that it went to study, that it tested its driving. So here's view looking at the scour marks here. Here's the first rock where they tested the laser ablation spectrometer. So they actually fire a laser at the points, and it vaporizes material off the rock, and that's how they get an estimate of the composition of the material. That's one of the ways that they do it. There's many instruments that do that. But you see, continuing to check, the wheels turn, deploying the robot arms. So they were all the way to August 20th, 24th before they even drove anywhere. But drive they did, and here you can see where they landed and where they drove, did a circle, proved that everything was working properly. Here's the first composition results of that rock here. Basically, it's a basalt, like what we expected. And then here's a view looking off into the distance once again, and this just shows you the distance views here. So this is how far each part of the foreground going off into the background is. So lots of things to see. But the quality of the rocks here, if you didn't know any better, you'd think you were up in Sedona or in the Grand Canyon, looking at the quality of the rocks that it's going to be exploring. So here's a view with the first initial drive. It made its way there. Here's a color view of the back shell and parachute, and just looking as it drives along the surface. Here's a good view of the lower deck of the rover, seeing how it's got pretty good clearance there. This is opening and closing the sample inlet containers there on the top of the rover deck. So continuing, this whole thing is just testing at this point, really. Testing each of the instruments and components of the rover. And making the drive over, studying rocks as it gets there. Now, there was a press conference in September of 2012, and it refers to these outcrops that were pretty near the landing site. And when they looked at it up close, they noticed that the pebbles that were composing this rock were very, very rounded. And if you know your geology, you know the way you get rounded pebbles is by banging them together in a stream. So this is called a conglomerate. Here's the Earth version, here's what they see at that location. So they suggested that there was substantial water flow at this site to bang these rocks into pebbles and to make this conglomerate type of rock. So that's a good sign that they landed in an interesting spot. October, the first use of the scoop into the soil, put it into your scoop, put it on your tray to look at it, and here's a dune where they scooped, and then preparing that to put inside. So it wasn't until November that they got their first results of X-ray diffraction, and this is also indicative of basaltic soil here that makes up this dune. Here you see, this is probably, you've seen this image in Science, I think it was on the cover of Science, or posters that were released by JPL that show the rover sort of looking on to itself. That was taken by the hand-lens imager, making that mosaic of the entire rover. Here you see this location here. It finally got to this location of these 3 different geologic units, looking at different components of that. And when they looked in detail at these rocks at this place they call Yellowknife Bay, very thinly cemented rocks. You have cross bedding over here. When you look at the rocks up close, you see they're fractured, and they have liquid water flow had produced sulfate minerals that actually fill the fractures in the rock. So very, very interesting. It wasn't until February of last year that they actually did their first drill. They extracted their first drill cores here and placed those inside the instrument. And they, so February 25th, they actually put it inside the instrument, and the first drill sample results came less than a year ago at this point here. And this is just basically describing it, but the gases that came out of this, you know, sulfur-rich, chlorine, some very interesting materials coming out. Did it say methanes? Does
Chloromethane?
Right, chloromethane, yeah. Mm-hmm.
Wow.
So, to make a long story short, this is basically a very different type of environment than what Opportunity studied at Meridiani Planum. The water that flowed and produced the rocks over there that produced the hematite and the jarosite and the other minerals there were very more acidic. But when you look at the rocks here, these were formed in more neutral environments. And this is hard to read, but this is just a comparison from the first drill results. This is Opportunity in Meridiani Planum. Hematite, spherules, magnesium sulfates imply acidic, briny waters not favorable for life. Here you get spherules and calcium sulfates plus smectite clay minerals. So once again, we have those clay minerals means that you had neutral pH waters favorable for microbial life. And the PI of Curiosity told me, you know, you could actually drink this water, although, yeah, I don't know if I'd go that far. But anyway, the exciting thing was that at this very first major outcrop that the Curiosity rover studied, haven't even started climbing the mountain yet, but they accomplished their primary mission goals. They identified an ancient habitable environment at this location in Gale Crater. Regional geology and fine-grained rock suggests that this site was the end of an ancient river system with an intermittently wet lake bed. The mineralogy indicates sustained interaction with liquid water that was not too acidic or not too alkaline and low salinity. Not strong oxidizing conditions. So the key chemical ingredients for life were all present in these rocks: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So this would have been a place where you could have had primitive biological organisms. Now since then, now this is jumping all the way to the December of 2013, so just 2 months ago, they had another press conference to try and do more description of this environment. So you have a small channel coming in. This would have been an alluvial fan, and this is where the intermittently wet lake bed would have likely have been located. And they have just more detailed information about a number of things, from the rocks, the ages of the rocks estimated based on radiometric dating, potassium argon age determination, about the clay mineral structure, and about the radiation environment. I'll talk a little bit more about the radiation at the end of the talk. Just some more views looking at some of the different outcrops there and trying to get a better understanding about how the outcrop was weathered and evolved over the time period. Okay, well here's the radiation slide here. So radiation exposure during the Earth-Mars voyage. So the Curiosity measured this, the cruise phase, from when it was launched from Earth until it landed on Mars. And the cruise, it accumulated 466 millisieverts. Now what that means is, in comparison, an astronaut's career lifetime radiation exposure limit is 1,000 millisieverts. That's common between the Europeans, the Canadians, and the Russian space agencies. And that implies that there's a 3% risk of exposure-induced death by cancer. NASA's limits are 600 to 1,000 millisieverts for females, 800 to 1,200 for males. So you're getting a significant fraction of an astronaut's lifetime dose just on the cruise out there, and then of course you have the cruise back. So what that means is if you're going to spend any abundant time on the surface of Mars, you're going to want to have some sort of radiation protection, or go to lower elevations where the atmosphere is thicker. So the mission, the Curiosity rover mission, is continuing. This red bar shows you where we're at. We're right at the end of the nominal mission, and now is going to be up to be eligible for an extended mission, where NASA cuts the funding but wants it to continue operating and continuing to do science, and it's going to have to compete with the other missions. So what do we have to look forward in the future? Well, I mentioned there's 2 rovers that are being planned in the future. One is the European ExoMars rover, and here's sort of a diagram about a model of what it looks like. It was a joint U.S.-European mission, but the U.S. backed out of that mission during the economic downturn a couple of years ago, so ESA is now working with the Russians to launch the vehicle. ExoMars will drill and analyze samples and then investigate catching or storing of the samples for eventual return to Earth. The U.S. has now gone back in and suggested in 2020 it do a Mars rover that would be derived from the Curiosity, except maybe powered by solar panels. It might be powered by an RTG. We'll have to wait and see. This will also most likely be a rover that will obtain and store or cache samples for eventual return to the Earth in the following decade. In other words, it'll be the first step of a Mars sample return mission. And the idea is you have a rover that catches and stores samples for some period of time. Part 2 of the mission you would send something that would land on the surface of Mars with a return rocket. The rover would go up to it, put the sample container inside this rocket. It would launch from the surface of Mars and go up to Mars orbit. And then part 3 of the mission would either be an Earth return vehicle would take that sample and return it from Mars to Earth, where it would land or be collected at the space station, or if by that time you have astronauts there, the astronauts who might be orbiting Mars would then collect the sample and then return it to Earth with them. So that all is for the future and has to be worked out. So in conclusion, robotic rovers are used for multi-site, mobile, in situ analysis of planetary surfaces and atmospheres. The Soviet Union had the Lunakhod rovers on the moon. Now the Chinese have put down their U-2 rover. They also had the Vega balloons in the atmosphere of Venus. The U.S. has had the very successful Mars rover program with Sojourner, Spirit, and Opportunity. And now Mars Curiosity rover is the next major step in planetary roving. It is a nuclear-powered, long-distance, mobile geochemistry and mineralogy laboratory. It's the most complex and expensive rover that's been built to date, costed about $2.5 billion. It has been deployed by the successful Sky Crane landing system, which could usher in a new era for robotic roving, because now with the Sky Crane we have the capability of landing about 1 ton robotically on the surface of Mars. Aerial and surface rovers are being designed for many targets. I've mentioned the one for the comet. I mentioned that they thought about it for Saturn's moon Titan as well. And I would say rovers will play a necessary part for any Mars sample return campaign to store samples for long periods and then drive them to their Earth return vehicles. So with that, I'll be happy to take questions, and thank you very much for your attention. Questions? Yeah. Mm-hmm.
I have a few questions.
Sure.
My 2 major questions is, one, since you're being able to prove that Mars, at least at one point, was habitable, is there ever going to be a mission to prove whether or not there was life on Mars?
Yeah, that's a good question. There's a couple of ways you could approach the problem. I think most people think that to answer that question and really confirm that, you would need to get samples from the right spot and bring them back to Earth where we can study them in our labs and we can really interrogate the samples with all the wide range of scientific techniques and instrumentation that we have here that cannot be miniaturized to put on a mission that would actually land there. So unless we were to have a mission that would actually just be fortunate enough to look in the right spot and see a fossil of something big, assuming that something like that did evolve on Mars, that would be a very I think most people think that's very unlikely. So I think the most likely method is, yeah, to take the samples and bring them back, and we'll confirm it or deny it that way. Mm-hmm. And your second question? You can ask the second question. Mm-hmm.
My second question would be, assuming you can land someone on Mars to get the samples and all that, would you go looking for the other rovers, the past rovers, even the Russian rover that they don't know?
Unless there was a compelling reason to do so, because if you're going to deploy humans to do it, you want to have the most robust justification for putting them there. They have to do a very specific task. You want to use robots to do the dangerous things as much as possible before you bring the people in. So if a sample return rover had collected a sample cache, but something happened and it couldn't return it to the return vehicle, then that might be a justification for a human mission for humans to land on the surface, collect those samples from that broken rover, and then bring those back. That's one possibility. I think the way most people are thinking about Mars right now is that, you would send humans into Mars orbit and maybe dock with the Martian moons Phobos or Deimos, which are really small, low gravity, they're more like asteroids. And then from that orbit, you can telerobotically operate rovers and other equipment on the surface, whether it would be to gather more samples or to do some sort of exploitation of Martian resources to begin building infrastructure for a base or something like that. If we develop the in-situ space resource utilization like what Al talked about a month ago, you could have astronauts in Mars orbit, maybe do something like that, build that initial infrastructure before you send people down there. So, but I would like to believe that we are going to send humans to the surface of Mars at some point. The question is why and when. Other questions? Yeah, Mike?
There's some lunar rover being worked on. It's sort of a NASA semi-private.
Yeah, there's a NASA connection. I just saw that. If you read Space News or Aviation Week in Space Technology, which I get in my lab, that's how I keep up on what the human side of things are doing. There's a relationship also with a Google Lunar X Prize about wanting to put NASA giving seed money to companies or a prize if they land something, a rover on the moon, I think is one aspect of it. And then there's some other aspect that's been in the news recently that changed about, I don't know, either length of time or maybe in situ resource utilization on the moon. Can you take lunar material and do something with it, do something instructive for building material? I think those are the two issues, and I think those have been in the news, space news recently. Yeah, Patrick?
Yeah, the Curiosity, what's it going to be doing, like going up the Mount Sharp? Is it going to kind of like over a course of months or a year or so?
Yeah, we're approaching the end of the nominal mission for Curiosity, which was one Mars year, which is 2 Earth years from when it landed. So, yeah, we're approaching 14. Yeah, so August of 14 would be the end of its nominal mission, and it'll be up for approval to do its extended mission. Now, it accomplished its main scientific objectives already, but there's still an awful lot that can be learned. And since all the science instruments and the rover is working perfectly, yeah, it's very likely that they're going to fund an extended mission. And yes, it will go find the best way through that dune field to get to the base, and then just slowly start going up, and studying those rocks as long as the thing is functioning, I would think. They do the extended mission. They look at them every 2 years, 2 Earth years. And as long as there's money available, and the spacecraft is still functioning, they usually approve that. But after every mission extension, they usually have to cut the budget back, and because the more, if you keep spending money on your active missions, you're getting good science per dollar because the missions are active, but that's less money to put into new missions. So that's the big controversy we have right now with the amount of money that's available. Are we going to be able to both do an first extended mission for, say, Curiosity to continue doing its thing, and then also fund the Cassini mission, which is orbiting Saturn for its last 3 years? So that's something that's going to be determined over the next year or so. Mm-hmm.
One more question. About a Europa mission, I know there's one Clipper that's going to like a fly.
The Europa Clipper, yeah. Mm-hmm.
What about a mission? Is there something in surface and go through the ice into the ocean?
That's interesting. The idea of the clipper was before you can land on the surface, you need to find the sweet spot. Where's the place that the icy crust is the thinnest? And so for Europa, the theory has been that you need to have this clipper mission that would do the same work as an Europa orbiter and characterize the icy crust of Europa, find where it's the thinnest, and that would be the ideal point to put an object that landed on the surface. However, in the month of December that was just passed, you might have heard the announcement that they detected, I believe it's from the Hubble Space Telescope, that water vapor geysers have erupted through fractures at Europa, I believe during the Europa South Pole. And the idea is when Europa is furthest from the sun and the gravitational pull of Jupiter is such that it actually causes extension and opens the fractures. So that liquid water ocean that might be habitable will then be communicating via these things. So you would want to consider whether you want to fly your Europa Clipper with the right type of instrumentation to see if it can detect life in that material that's coming out. So you may not even have to land on the surface to answer that question. That's another thing that's, since that just came out, that was just announced in December, so that's something that NASA is looking at in the Outer Planets community in our concept designs for the Clipper. Do we need to adjust the instrument suite any for that option? And then the science people who made this discovery are trying to verify it by other observations. Yeah, Chuck?
On Europa, can you explain if there's life in that ocean, where does it get its energy from? Is it from Jupiter? Or?
Well, it'd probably be some sort of a chemosynthetic autotroph. It'd probably be something that would get its life through the hot fluids coming from the interior. The base of the ocean percolate through. It's like the black smoker type of life that's deep on our own ocean floor. So, that is life that doesn't get any energy from the sun. It gets the heat, the energy, the nutrients from the hot fluids that erupt out of the vents on the ocean floor. And you have whole communities of life, different types of life that have evolved around that don't require any exposure or any energy from sun or photosynthesis to survive.
They get it from deep from
Yep.
Earth. So Europa has a molten center?
One would think so. When you think about Europa, it gets its heat from tidal heating. So the icy crust of Europa flexes about 40 meters every 3 days or so. Really? So that, just like Io, it flexes 100 meters every 48 hours. So Europa is the same, and since it's a more icy body, that's what generates the tidal heating that melts the ice to form the liquid water ocean. So you have the heat, and you have organics. We've detected organics with a lowercase o. All the elements appear to be present. So if you have the heat, you have the liquid water, and you have all the ingredients for life. And now we have a way to interrogate that material now that it's coming out in plumes.
I thought I just heard about some discovery in our polar regions of some sort of life that lives attached on the bottom of icebergs or
Yeah, there's frozen lakes and things that project down into these cold waters, and they have found some sort of a life that exists like that. So
underneath the ice.
Yes. So the more you look at the extreme environments on Earth, we're finding more and more evidence of life in some form that can exist on that. So it's becoming that. And then they also in December. Or early January, they announced that there's also plumes on the asteroid Ceres. So those were detected, I think, by the European Herschel Space Telescope. So what does that entail? Is there liquid water? Is there a frozen lake? We'll have to wait for dawn to find out. But that's something that's we're thinking about too. Mm-hmm.
One more question.
Sure.
Because I got like a million of them, but I want to give everyone else a chance.
Mm-hmm.
My other question, if you're able to explore by some miracle all the planets in our solar system and all the moons and all that, would there ever be a chance of going outside our solar system and looking at potential life outside of our own solar system? Potentially,
but we have a whole part of our science division in the astrophysics division at NASA that is focused on exoplanet studies. Matter of fact, one of our faculty, at least one, probably more of our faculty at ASU are focused on exoplanet research, and they're developing new techniques that you can do from Earth orbital or near-Earth spacecraft that can do very refined studies to identify planets around other stars in our galaxy and getting more and more information. You know, what kind of elements might they have? What kind of temperatures exist on the surface? Could liquid water exist? We found locations where we have oxygen. I don't know if we've confirmed that there's water in the form of ice yet. And then, of course, suppose you looked at a spectrum from an exoplanet and you saw chlorophyll. Well, there's the answer, that you have life someplace else. So the answer is yes, we are developing the techniques to help answer that question, could habitable planets exist elsewhere in our galaxy? And we've already found many, many Earth-sized planets that exist within habitable zones around other stars, thanks to NASA's Kepler mission. And then the new missions that are on the drawing board would refine those estimates even further. Now, whether you would want to send a space probe out there, of course you could, but it's going to take a long time to get there. I think, for our current state of technological development, you're better off, using our resources and just looking at the light and, signatures coming from these bodies and then answering the questions that way.
The next generation of telescopes are, going to be showing us a lot more stuff.
Yep. Yeah, there's talk about using the James Webb Space Telescope, the next big thing to replace Hubble, which will theoretically launch in 2018. That would be put out at Earth's L1 point, and it would have the capability to do some additional types of studies. But there's other telescopes and missions that are being proposed both by us and the Europeans that would help that even further.
The optics before they send it out there, right?
Yeah, exactly. Other questions? Does anybody else have any other questions? Yeah. Mm-hmm.
I have one that's a little off of what we've been, but you showed was that a comet back there? That picture, that small body? Orbit or something? Series.
Yeah, well, the posters back there are Vesta. That's one of the second largest asteroid in the main asteroid belt between the orbits of Mars and Jupiter. That was the first target of the Dawn mission was Vesta, and now it's on its way to Ceres, which is a dwarf planet, largest asteroid.
The issue I have just curiously, what's the escape velocity? I mean, could you jump into space from Vesta?
Yeah.
Well, the escape velocity, let's see, the gravitational acceleration on Vesta is 0.25 meters per second squared. As far as the escape velocity, that I don't remember.
You could jump off it.
Not Vesta or Ceres, but there are other asteroids you could jump off of.
An object the size of Camelback Mountain.
Yeah.
Maybe
Yeah.
you could jump into space.
Yeah, definitely.
You have to be careful.
That's right. Well, that's one of the issues, about astronauts, and President Obama, instead of going back to the moon, proposed this asteroid retrieval mission where we would take a near-Earth asteroid, theoretically with useful resources, and sort of capture that and bring that back to Earth-Moon L2 and the second Lagrange point, and then learn how to work with a low-gravity body in those type of environments. So, there's a whole debate about whether that versus going to the moon versus going directly to Mars, what the human spaceflight program should be doing. But there are certainly issues about learning how humans would work with low-gravity bodies like that are very important questions that need to be answered. Yeah? Mm-hmm.
This isn't exactly a science experiment, but it kind of goes back to your slides where you're talking about no instruments able to confirm life. What I'm curious about is on the original Viking landers, people have argued, or at least a few people have argued, that there was a positive life reading on one of the instruments for years. Is attention to the detail in your slides, because they actually get a certain amount of questions about were there decisions made for or again, including certain instruments on the basis of not wanting to make ants.
It's the way you think about it and the way you design missions, because usually you approach it from two different angles. A mission is proposed, and from that you have a list of scientific objectives and questions that you want to answer. From that, you determine what kind of measurements you need to answer those questions, and from those measurements you think, what are the best instruments that you need for that? And then each of those instruments comes with a power and a cost and a mass requirement. On the other side, you have the amount of money you're getting given from the government. A mission will cost this amount. And then working with the engineers, what kind of mission architecture do you need? Do you need a flyby, a rover, a lander, a stationary lander, or orbiter, or whatever? and you sort of merge those two and meet in the middle, and that's how you design a planetary mission, something that fits the cost cap, that has the right instruments, that makes the measurements, that answers the science questions. Now, with this thing you cited about the Viking landers had 3 experiments that were designed to search for life in the soil there, and in terms of the answer, 2 of the 3 yielded positive results. However, it's the consensus of the science community that those positive results were due to the complexity of the Martian soil that hadn't been anticipated when those instruments were designed. So it's like we wanted to ask the question, does the soil of Mars have life, expecting an answer of yes or no, and instead Mars replies, could you ask the question again? Because the instruments weren't optimized for the complexity of the Mars soil, and now we know that the solar radiation that strikes the soil of Mars, it oxidizes the soil, so the upper layer life can't exist. You have to be down deeper, below that in an environment where maybe microbial life could exist or preserved or something like that. It modifies the soil and produces perchlorates and other things like that. So in the very top soil that's exposed to the environment of space, no, there won't be life there. But that doesn't mean that down below that, but down below the cryosphere, where you have the rock and the dust below that at the polar latitudes down, to the mid-latitudes, you're going to have ice preserved. Below that, particularly if you have a hot zone, a hot spring there, that might be a location to look, if you can find that. Mm-hmm.
Kind of on that note, I know some of the methods and stuff. I'm kind of curious if maybe there's something else that I don't know in terms of sanitizing a rover, so if we don't bring something over to the other planet and contaminate it.
Yep.
With life.
NASA has a whole division called Planetary Protection, and it has 2 functions. One is that devices or spacecraft that land on other planets' surface have to be sterilized to a certain degree to prevent any Earth microbes for getting to the surface. The other side of that coin is that any material that's brought back from elsewhere in the solar system to Earth has to be contained in a type of environment so that there's no chance of contaminating Earth with anything like that. So every NASA mission has to review planetary protection guidelines depending on the nature of the mission. And for anything that's going to land on a potentially habitable world, like, say, Europa, they have very, very stringent guidelines. Mars, they did have to a point, but they think that if there might have been microbial life from Earth on the Russian missions that might have contaminated it at this point. But we don't know that for sure. But there's still pretty stringent guidelines for NASA missions that go down to the surface of Mars.
I'm more curious about, do you know some of the methods, like irradiation?
Yeah, you can use irradiation, you can use heat. You heat your instrument up to something that would cause the breakdown of any type of living organism that we know of on Earth. You can use alcohol wipe and cleaning. They're all produced in clean rooms, so astronauts or engineers working on the building of these instruments all are wearing gloves and things, so there's no direct physical contact between human biomass and the instruments, things like that. Mm-hmm.
If you do that, though, aren't you potentially ruining the sample? Any of those methods? Couldn't you potentially ruin the samples that you're bringing back?
No, what you would do in the case of a sample return was you collect it in its natural environment and you have it in a sealed container, and then it's brought back. And most of the way that we brought back samples since the Apollo program, they have been inside these multiply sealed containers that have been put on probes that have entered the Earth's atmosphere, and then they parachute and land in the Utah desert, and then those are taken, you take the thing off, you put it in a truck, you take it to a lab in a clean room, then you start removing the different layers until you get to the container that has the samples, and then you're opening that in a clean environment. So those cleaning methods that I described for things that are going out there, there's a different methodology for when things are brought back.
Is that how they did it on Apollo as well?
Yeah, I don't remember the details of it, but yeah, you had the samples and all that stuff. And now they got back into the lunar module, the part that launched off the surface of the moon. They still had their spacesuits, which were covered in dust. They left those behind in many cases. I don't know in all cases. I think there's some in the Smithsonian or someplace on that thing. And then they came back in the command module they brought the rocks, but there had to be lunar dust on the bags and things like that. And then those things landed in the ocean. They opened up, and they got the astronauts off. And
wasn't there some talk about, I mean, back then, some talk about bringing microbes back to the Earth?
Yeah, and that's why they put the astronauts into that RV unit they were supposed to stay in for 3 days to make sure that they didn't get sick or anything like that. And then they had the doctors all check them out. So, yeah, I wouldn't worry about that as much coming from a body that's airless, that's exposed, and the heavy radiation from the sun. Yeah.
The Andromeda strain is not going to survive that.
Yeah, I've actually never seen that movie. Shame on me, but I wouldn't worry about that. Other questions?
I think we'll wrap up. I'm sure Professor Williams will hang around for a while. We can chat and ask questions. So, again, thank you very much. It was excellent.
You're welcome.